All right, so we've been talking about our ability to calculate how much heat goes into something or how much heat is lost by something by looking at either changes in temperature or changes in phase. And this graph right here that you're seeing is called a heating curve. You can see across the x-axis here, heat is added at a constant rate. So as time goes by, heat is added at a constant rate. So perhaps it's sitting on a hot plate, or maybe it's being heated by a Bunsen burner, something of that order in our lab. On the x-axis, on the y-axis, you can see we have temperature in degrees Celsius. So the graph starts down here at minus 20 degrees Celsius. And we're talking about water in this case. So water, under normal pressures, is a solid at minus 20 degrees Celsius. So as heat is added at a constant rate, what's going to happen is you can see the temperature is rising, 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 rising until it gets right here, which corresponds to 0 degrees Celsius. Heat is still being added at that same constant rate. But you can see for a while here, the graph remains flat. So solid water is being converted to liquid water. So it is along that flat line there, it's melting. So that would be the melting point of water, and again, under normal pressures. So 0 degrees. So you can see it's flat. So then once again, right here now, right here you have ice and water, they're saying. So you have an equilibrium, which we talked about, between the solid and the liquid phase of water. All right, so now the temperature is going to start rising again. So heat is still being added at that same constant rate. And now the temperature is rising, 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 rising until, again, it stops rising right here at 100 degrees. And then the graph remains flat again for a while, as that heat is still being added at the same constant rate. But now we've reached another phase change. So you're going from the liquid phase up here to the gaseous phase, or the vapor phase. And this would represent boiling, where the liquid and the gas phase are in equilibrium with one another. And then once you get to this point right here where the temperature starts rising again, now you have all gas, and it would increase in temperature again. All right, so how are we able to calculate these heat changes and the amount of heat that is going in? Well, there's two formulas for that. So the first one should have been right there, and I don't know what I did with it. Oh, well, looks like I'm writing it. I don't know what happened there. All right, let me bring up another one then. All right, so the formulas are, when you are changing temperature, Q is equal to mc and delta T. And when you're changing phase, Q is equal to m and a concept called delta H. All right, so let's explain what each of these are. Q is heat. And heat, in this case, is going to be measured in a unit called joules, which is capital J abbreviated. Or you could change it to kilojoules if it is, greater than 1,000. We like to do that. M is mass. And the mass is normally given in the unit grams. Having problems with my pen. Time for a new one, I think. C, I'll come back to C in a second. Delta T is change in temperature. So change in temp measured in degrees C. All right, so this concept of the specific heat, I showed you a few demonstrations with this, and it is called the specific heat constant. All right, so the specific heat constant is measured in a unit of joules per gram degree C. So it is the amount of heat, joules, it takes to raise the temperature of 1 gram 1 degree Celsius. And you could look it up in a chart. For water, it's crazy high, as we've been talking about, 4.18 joules per gram degree C. For most metals, it's something around 0.1 up to maybe 1, or aluminum's 0.9. So this is a range of metals. Somewhere in there, usually, most metals are found. So you can see if you have a metal it has a low specific heat, and what that translates into in our calculations is you don't need as many joules, or you don't need as much heat in order to change the temperature. The higher the specific heat, like water, the more joules you need to change the temperature. So it requires a lot of energy to change the temperature of water, in other words, compared to that of aluminum or copper. And that's a concept that we understand. We put plastic or wooden handles on our pots that we cook with because then we can put the metal in direct contact with the flame. Temperature changes fast. But the handle itself remains kind of cool because it would be made out of a material that would have a higher specific heat. So the temperature of the material is not going to be very high. It's not going to conduct the heat as well. All right, so over here we have Q is equal to M delta H. We save these calculations for when we change phase. So phase change. As I said, my pen is frustrating me. Q is still heat, still measured in joules. M is still mass, still measured in grams. Now, this concept right here is called the enthalpy. And different than it is a change in enthalpy, as you can see with the delta. We're going to do some things about thermodynamics later in the year, or even next year with advanced chem. We do quite a bit more. But essentially, you look this up in a chart as well. So this is just like this. It's going to be a constant. And what we have to watch when we do this is two things. It's either going to be in joules per gram, in which case we would leave the mass in grams. But you do see sometimes it listed as kilojoules per mole. So then we got to do some chemistry calculations. We understand that. If we have grams and the constant is in per mole, then we can't use the grams, obviously, because it won't cancel. And so we have to do a preliminary calculation changing grams to moles, which we are experts at. All right, so going back to this, let's try a problem, and I think you'll find that the calculations are not very difficult. All right. Change color. All right, so how much heat is needed to raise the temperature of 55.75 grams of liquid water from 13.5 degrees Celsius to 75 degrees Celsius? And then down here you can see I've given you the constant. The specific heat of water is 4.18 joules per gram degree C. All right, we're changing temperature. So Q is equal to mc delta T. Heat equals mass times that constant times the change in temperature. And the change in temperature is always given as the final temperature, so where it ends up, minus the initial temperature, where it started. Okay, so it's basically just plug the numbers in. So Q is equal to the mass, 55.75 grams. The specific heat, 4.18 joules per gram degree C. And the change in temperature, final temperature, 75. Minus the initial temperature, 13.5. And just calculate. My old high school teacher called these plug and chug. So you plug it in the formula, chug it out of your calculator, no real thinking involved, as long as you put stuff in the right spot. So 55.75 times 4.18 times 75 minus 13.5. Remember the algebra, you have to subtract this first, then multiply. But with my calculator, I can put the parentheses in, and it does that for me. So 14,332 joules. We don't want a number that big as an answer. Anytime it's greater than 1,000, I like you to change it to kilojoules. Plus, it's way too many significant digits, although we're not going to be too focused on that. But each of the numbers, you can see we have a 3, a 3, and a 4 up there. So really, we should change this to 14.3 kilojoules. So move it 1, 2, 3 to the left, or divide by 1,000, and you get 14.3 kilojoules. So that's how much energy would be needed in order to change the temperature of water from 13.5 up to 75. All right, next calculation. How much heat is needed to melt 150 grams of ice? Now, there's two different kinds of delta H's. You'll see a little abbreviation after the enthalpy. Fusion would be when you're melting or freezing. And we're going to talk about the sign when we do the next calculations. And then the other one would be vaporization. So vaporization would be when you're boiling or you are condensing. And I know you can't really read that very well, but sorry, like I said, my pen's frustrating me. All right, so how much heat is needed to melt? So now we're changing phase. Q is equal to M delta H. The delta H in this time is given in grams as the bottom number, and so we don't have to worry about converting. Q is equal to the mass, 150.0 grams, times 334 joules per gram. Grams cancel, 150 times 334, and we get 50,100 joules, or 50.1 kilojoules. Again, greater than 1,000, change it to kilojoules. All right. Let me do one more. And that would be, sometimes it's not explicitly stated. Let me come up with a new one again. That you are changing phase. For example, let's say you have ice at, let's say, minus 10 degrees Celsius. So minus 10 degrees Celsius. And the question says, how much heat do you have to add to change that ice to 50 degrees Celsius? All right, so we have to understand that when you are at minus 10 degrees Celsius, water is in the solid phase. When you go to 50 degrees Celsius, water is in the liquid phase. So we actually don't just have one calculation here, we have two. Because the first thing we have to do is change that solid from minus 10 degrees to its melting point, which for water we understand is 0 degrees Celsius. So that's going to be our first calculation. Once we get to 0 degrees Celsius, now it's going to melt. So the next thing we're going to do, it's going to stay at 0. Remember the flat part of our graph. The second calculation is it's going to melt. Then the third calculation is once it's all melted, it will increase the temperature until you get to 50 degrees. So we have Q is equal to mc delta T, changing the solid water. So we need to know the specific heat of ice, which is not the same as the specific heat of liquid water. Then Q is equal to m delta H, where we melt. And then Q is equal to mc delta T, where we change the temperature again. All right, so I didn't give you a mass. Let's just say it's 100 grams. All right, so Q is equal to 100 grams times the specific heat of ice. The specific heat of ice you would have to look up in a chart, but it is 2.06 joules per gram degree C. So you can see it's actually less energy to change the temperature of ice than it is to change the temperature of liquid water. All right, so a mass times the specific heat, change in temperature. Final temperature, 0. Minus the initial temperature, negative 10. So 0 minus a negative 10 is 10 degrees Celsius. So we'd have 100 times 2.06 times 10. And that would tell us how many joules we would need to change the temperature of the ice. All right, so now we have the ice at 0 degrees. So now it's going to melt. Q is equal to M. Still 100 grams. All 100 grams is now in the liquid, or in the equilibrium between solid and liquid because we're melting. We need to know the delta H for water. Again, we looked that up in a chart, or you'd be given it in the problem perhaps. And it is 334 joules per gram. So 100 times 334 will give us how many joules it takes to melt. So it takes 33,400 joules to melt the ice. So we've changed it from negative 10 to 0. Now we've melted it all. So now it's in the liquid form. I'm going to do this one down here. So now we have, once again, 100 degrees. Q equals, or 100 grams. The specific heat of liquid water, different than ice. Again, you look it up in a chart. Change in temperature. Started at 0, ended up at 50. So 50 minus 0, final minus initial, is 50. So 100 times 4.18 times 50, and we got 20,900 joules. So now, to answer the question, how much heat is needed to raise ice at negative 10 to 50 degrees? It would be that plus that. So this one plus this one plus that one. So all you have to do is add the three values together, make sure they're all in the same units, and then, like I said, I would probably change that to kilojoules. All right, so that's heat calculations.